to store those things. And it's interesting at least to mention how they did that. They introduced in the token something called a link token. And basically what that means is that a token can have a flag set that says that this token is basically a lower level token of an administrator or something like that. So it would set a bit in a bit field, flag field, and it would set a pointer to another token that is the actual token of the system administrator with the privileges of the system administrator that have been restricted. And as you remember, the process can't itself change its primary token. So they also introduced a new service running with system privileges called the app info service that is triggered by the Windows GUI or the Windows shell when it, for example, sees that this might be a setup program that you're running, or you're trying to copy files to a directory which you're not allowed to write to. And the Windows shell or Windows UI components would then call into this app info service saying, we need to request elevation for this particular thread that wants to copy files to a protected directory or something like that. And the app info service would then, first of all, switch to the logon desktop, protected desktop, and display the credential prompt. And for a logged in administrator, this would actually not be a credential prompt. It would be a consent prompt that you've all seen if you've run as admin on Vista, which has a continue and a cancel button. If you've got an application that actually needs admin privileges, such as a setup application or something like that, then there's a method of requesting the admin rights to be enabled. So basically triggering this elevation process. And that's controlled by a key in the manifest of the executable. By the way, all of this material is written up in a far more eloquent manner than I can present today, being jet lagged and all, in the white paper that you'll find both on the conference DVD and hopefully as well on the conference website after the conference. So I encourage you all to go read that afterwards. So enough about that. As a side effect of UAC, we now have processes running on the same desktop that might have different access tokens of different privilege levels. So you might have some that are running as a standard user and some that have been elevated that are running as domain admins on the same desktop. And if these processes have Windows on the same desktop, they can also post messages to each other's Windows message queues, which, as I said earlier, can lead to some security problems. For example, there are some messages that, when handled by the default handler, basically are treated as a function pointer and redirect execution to an arbitrary memory address, which is quite nasty. And to try to mitigate this problem, Microsoft introduced a feature called UIPI, or User Interface Privilege Isolation. And it implements a kind of filter of approved Windows messages that can be sent between windows at different integrity levels. So, for example, if I were to exploit a vulnerability in Internet Explorer or a plugin of Internet Explorer and get access to that process, of course I have a window open on the user's desktop where he might have some other applications that's been elevated to domain admin privileges. But since the protected mode of Internet Explorer is running as low IL, it can't send anything but benign messages that are on this whitelist to other processes of higher integrity level. And this message filter can actually be changed. using change Windows message filter, oddly enough. But of course, processes that are at low integrity level or below that level can't use this API. So it's interesting to know that it's there. It does give you some kind of protection if you're using mandatory labels to restrict a low privilege process from tampering with the rest of the system, but otherwise it's not that interesting. Right. Before I go on to specific counter-exploitation measures that Microsoft has developed during the years, I'll just put in this slide here just to make sure that everybody knows how memory protection works on Windows. Basically, your Intel hardware can enforce access permissions on a memory page basis. So on x86, a memory page is 4K. And each 4K physical memory page has a bit field with basically 3 bits controlling access to that page, saying, is this page allowed to be read, written, or executed? And the CPU will check these bits before reading, writing, or executing data from this page. And if these permissions are, if rather you try to read from a write-only page or write from a read-only page, or you try to execute from a page that doesn't have the X bit set, it will raise a page fault for the system to take care of, and then Windows can step in and say, well, you've done something wrong. And in the old days, you'd have the infamous GPF, and in these days you get an exception, and if the exception isn't handled by the application, then Dr. Watson steps in, and you get the Microsoft crash handler. These memory protections are set when you allocate memory. And usually you're probably using some kind of heap handler to allocate memory, but it all boils down to these functions. Virtual alloc, which allocates memory on a page-by-page basis. And when you call virtual alloc, you can also specify the page permissions for that particular chunk of memory that you're allocating. And you can also change page permissions for an arbitrary range of pages using the virtual protect call. Right, no more about that. Let's get to exploit mitigations. Since the Trustworthy Computing memo of Bill Gates back in 2002, I think it was, Microsoft worked very hard at both improving the security of their code, but also improving the resilience to exploitation. So some of the mitigations that they put in place in their toolchain and in Windows are interesting to application developers, because some of them you actually get a lot of protection for free without doing anything. Some of them you actually have to be aware of and make use of and enable yourself for them to be effectively protecting your process. So we'll start with GS or stack overwrite protection. This is one of the first exploit mitigations that Microsoft put in place, and it's developed quite a lot during the years. So with each new release of the toolchain with Visual Studio, it gets better and better and harder to circumvent. And it basically works by pushing in a cookie value in each stack frame and making sure that when you return from a function, that this cookie value is intact, that it hasn't been overwritten by, for example, a stack buffer overflow. So it protects the return address from a standard stack buffer overflow vulnerability. And it also protects overwriting stack variables. So if you've got a memory pointer on the stack, for example, that could be manipulated by a buffer overrun, that could be protected as well. And this has been a default compiler option, actually, since Visual Studio 2003. So if you're using latest version Visual Studio, latest version of the Microsoft toolchain, you're probably already protected by this, if you haven't switched off, that is. But buffers can not only be on the stack. Larger buffers are more often allocated on the heap. And there have been a lot of talks recently at recent Blackhat conventions about exploiting heap buffer overflows. So just as with the /GS protections in the toolchain, in Windows, in the default heap handler, Microsoft have implemented some exploit mitigations to try to prevent a buffer overflow on a heap allocated buffer from becoming a large security problem. So the first thing that they did was implement checking of forward and backward links when unlinking chunks or allocated regions in the heap. So basically in a standard heap manager you would have linked lists of blocks of memory that are either on the free list waiting to be allocated or on the allocated list. And when you call free, they're taken out of the allocated list. And when they're done, when you're doing that, you're basically just unlinking it from a doubly linked list. So you've got forward and backward links that are spliced in to. And if you can overwrite this metadata on the heap, then you can actually use that to write arbitrary values, overwrite arbitrary values in memory. And an easy check is just to check that the forward and backward links are actually pointing to two chunks that are pointing back to the original chunk to make sure that the links you're following aren't being forged. And that was implemented in XP, so SPAC 2. But there are more advanced protections in place in Vista, for example, and later versions, such as encrypting, or rather obfuscating metadata, and using checksums to validate the integrity of metadata, other than just the forward and backward links. And these you actually need to enable, because they aren't enabled by default. You have to set with the heap set information API call and the heap enable termination on corruption information class. You can enable these protections so that when heap corruption is detected by these exploit mitigations, your process will die instead of being taken over by an attacker, which is infinitely more preferable to us security people. So there's something you need to be aware of as a developer, that each process needs to, in its initialization routines, call this API call to enable these protections. And of course, don't use your own malloc. Don't use your own malloc implementation. Don't use your own heap handler, because you won't be protected by these exploit mitigations in the default Windows heap handler. So, for example, Adobe got bitten by this in Flash, I believe. They had their own old malloc implementation statically linked in, which had all of these, which had none of these features, rather, and was wide open to exploitation. Whereas had they just used a compatibility layer that forwarded all of this down to the default Windows heap handler on the platform they were